Welcome to the Deep Dive, where we take cutting-edge research and really extract the crucial insights you need to know.
Glad to be here.
Today we're diving into this constant pursuit of high-performance materials. I mean, it never stops, right? Especially for aerospace and automotive.
Never. There's always a new frontier.
And we're talking about aluminum 7075, or Al7075. It's a workhorse alloy. It's already known for its superb strength-to-weight ratio. So the question is, why are researchers pouring all this energy into fundamentally changing something that, already works so well?
Because in engineering, well enough is never really the end goal, is it? We're always looking for that optimal blend of properties.
The perfect recipe.
Exactly.
Yeah.
Al7075 is a benchmark, no question. But if we can tweak its internal structure, if we can make it even a little bit lighter, stronger, or tougher, that creates a massive competitive advantage. Our material stack today is all about finding that balance by introducing a very, very precise modifier.
And that modifier is nano-sized magnesium. We are dissecting a fascinating experimental study that did just that. They modified Al7075 by adding varying percentages, up to 2.5% using the stir casting method.
Right.
And our mission today is to uncover the really extreme trade-offs this creates. We're looking at 4 things: mechanical strength, wear resistance, corrosion, and fracture behavior. And here's the crucial point right up front. This deep dive is about strength at a severe cost. We're going to show you how a gain in strength is accompanied by a shocking 35% loss in a different vital property.
And that severity, it really all hinges on our modifier magnesium. For context, it is the lightest structural metal available. It's about 33% lighter than aluminum.
Wow.
Yeah, and it's essential for strengthening a lot of existing aluminum alloys. What's also really interesting about magnesium, just in general, is its use in biomedicine. Its elastic modulus is similar to human bone, and it's biodegradable.
Oh, that's fascinating.
Yeah, so it's perfect for things like temporary orthopedic implants. But here, in this study, we're using its structural properties to fundamentally alter an alloy's performance.
Okay, let's unpack this. Let's start with the fabrication. Why the nano-sized particles, and why stir casting? What's special about that method?
Well, the nanoscale is the key. We're talking particles between 30 and 50 nanometers. It's all about ensuring an ultra-fine distribution throughout the melt.
So getting it mixed in perfectly?
Perfectly. And stir casting, where you melt the alloy and you're just continuously agitating it while adding the nano-mg that forces the uniform dispersion. And that's a huge challenge, because metals typically don't like to mix perfectly.
So it's not just about mixing the elements, but integrating them on a scale that actually forces microscopic changes?
Precisely. And once that NMG dissolves and integrates, 2 crucial things happen at the microstructural level. First, you get an overall reduction in the alloy's density.
Just because magnesium is lighter?
Simply because it's lighter. A great starting point for aerospace. Second, those dissolved NMG particles act as nucleation sites, which leads to massive grain refinement.
And grain refinement, that's the core mechanism for strengthening, right?
It is. Think of the material's internal structure as being packed tighter. It also increases something called dislocation density, which just means it gets harder for the material to deform under stress.
Oh, okay.
If you have many, many small grains instead of a few large ones, it's like trying to move a crowd through a maze full of small, intricate barriers instead of just a wide-open hallway.
I like that analogy.
By hindering that crowd movement, or, dislocation movement, the alloy becomes inherently stronger.
So that microstructural tightness sounds promising. Did it actually translate into measurable gains in strength?
Oh, absolutely. Looking at hardness first, the modified alloys showed really impressive improvement. Researchers recorded a maximum hardness gain of 15.73%.
15.73. That's a solid number.
It is, and that gain is directly attributed to the formation of these hard, brittle Mg phases that are now uniformly distributed inside.
Okay, that's a great improvement. Now let's talk about tensile strength, the alloy's ability to withstand being pulled apart.
Right.
The study found a maximum improvement of 9.21%. Significant, but what physically changed inside the metal to achieve that much stronger resistance to failure?
That 9.21% is caused by a kind of chemical marriage between the aluminum and the magnesium. You get the formation of the Al3Mg2 intermetallic compound.
Okay.
This compound is evenly dispersed, and it's these specific particles that act as the physical barrier to dislocation motion. They're just rigid, so they require far more energy to break or deform the material.
And this is where that engineering sweet spot emerged. The greatest strengthening effect, a peak tensile strength of 152 megapascals, that was seen at 2 weight% of nanomagnesium.
And here's where it gets really interesting.
Uh-oh.
They push past that optimum. When they went to the highest concentration, 2.5 weight%, the results, they actually got worse.
They dropped.
Both hardness and tensile strength dropped compared to the 2% sample.
Why would that happen? If more magnesium means more of that strengthening compound, why would the strength suddenly decline?
It's a classic case of overkill. You get something called grain coarsening. At these excessive concentrations, too many of those Mg-rich intermetallic phases form, and the Al3-Mg2 particles essentially start clumping together.
Ah, so they stop being efficient.
Exactly. Instead of many tiny efficient obstacles, you end up with fewer, larger, inefficient roadblocks. This actually reduces the alloy's ability to resist movement and deformation. And the visual fracture analysis backed this up. The optimized sample showed tearing ridges and dimples, which is consistent with increased strength, while the base alloy showed these brittle cleavage facets.
So we've established it. The optimal dose for strength is 2 weight%. That 9% gain is impressive, but strength only matters if the material can actually survive in the real world. Let's pivot now to the potential price tag of that rigidity. Toughness.
And this is where the dilemma really begins.
Yeah.
When researchers measured impact strength, so the ability to absorb a sudden shock before failing, the results were dramatic and concerning.
How so?
As the impact content went up, the impact energy went down significantly.
Specifically, we're talking about a massive drop here. The impact energy fell from 28 joules in the base alloy down to just 18 joules in the modified samples.
Yeah.
A 35% reduction in the material's ability to absorb shock. That's not a compromise, that's a structural casualty.
It really is. And the very mechanism that delivered that 9% tensile gain is what caused this 35% toughness loss, those rigid, brittle, intermetallic compounds.
The ones that were so good at blocking deformation.
Exactly. They also make the alloy much more prone to sudden catastrophic fracture under a dynamic load. You've basically traded elasticity for pure stiffness.
That major drop in toughness is worrisome for any component that has to withstand vibration or sudden impacts. But before we write this whole thing off, there was a clear counter victory in the durability section, right? Wear resistance.
Yes, the wear results were extremely positive. They showed an 18.82% improvement in resistance.
Which is great.
And this ties right back to the increased hardness we talked about. It follows Archer's law, wear is generally inversely correlated with hardness. The finer grain size and the rigidity of the modified alloy made it far better at resisting surface loss from, abrasion and friction.
And the material even helps itself out, doesn't it?
It does. A neat little feature they observed was that the beta phase within the modified alloy functions as a kind of solid lubricant, which further reduces wear loss. However, the SEM analysis of the worn surfaces still showed clear scratch marks. This confirms that even with the added protection, abrasive wear, so hard particles separating and scarring a surface, that remained the primary way it was degrading.
All right, so we've weighed the strength gains against the really tough costs. Now for the final and maybe the most challenging factor for any structural material, especially in aerospace, corrosion.
Here we find the biggest Achilles heel of the modification. The study found that corrosion resistance worsened noticeably as the NMG content increased, almost across the board.
That just sounds counterintuitive. Why does adding magnesium, which is so structurally helpful, suddenly make the aluminum base so much more vulnerable to breakdown?
It all comes down to basic electrochemistry. Magnesium behaves anotically compared to aluminum.
Okay, break that down for us.
To put it in simple terms, the magnesium acts like a sacrificial battery, or maybe a fuse wire, inside the aluminum structure. It's just chemically more reactive. So when its concentration goes up, that increased reactivity means it will break down first. And in doing so, it rapidly speeds up the destruction of the alloy's natural protective layer.
Which is the aluminum oxide coating.
The Al2O3 coating, exactly.
Mm-hmm.
So the magnesium is sacrificing itself, but in doing so, it creates all these weaknesses across the entire surface.
And they tested this.
They did. They submerged samples for 30 days in Pondicherry seawater. The visual evidence was stark. The SIM analysis showed dramatic, localized corrosion pitting, cracks, uneven surfaces everywhere. It was a clear confirmation that the passive coating had just collapsed.
And the culprit here is something you called microgalvanic activity, right? Can you simplify that for us?
Sure. If the anodic behavior is the overall problem, microgalvanic activity is the localized mechanism. You have these tiny, isolated electrical differences, like little self-destructing battery cells, between the aluminum matrix and those rigid Al2MG3 phases we talked about earlier.
The same ones that gave it strength.
The very same ones. These micro-interactions accelerate the breakdown of that protective layer, and that's what creates those deep pits and cracks you see on the surface.
So what does this all mean?
It means we have defined a profound engineering trade-off. The modification with nano-MG, it absolutely achieves its goal of dramatically improving key mechanical properties. The 9.21% strength gain, the 18.82% wear resistance, those are tangible benefits.
And the optimum strength dose is at 2 weight percent.
Right. But that high performance comes at the expense of two critical vulnerabilities: a massive 35% reduction in impact toughness and a significant acceleration of corrosion.
So that 2% modification, it might look fantastic on paper for a static structure where you only need maximum specific strength.
Right.
But the moment that component faces dynamic impact loads, or you put it in a corrosive environment like, say, a component used near coastal seawater, this study shows that modification actually introduces new failure points.
That's the challenge ahead. The next frontier has to focus on balancing these needs. How do we keep the impressive strength and wear gains without incurring that 35% toughness reduction or the accelerated corrosion? The answer probably isn't in changing the mixture anymore. It's more likely in post-modification solutions.
Like what?
Well, could specific surface treatments like specialized coatings protect the alloy from that anodic attack? Or maybe we could use targeted phase manipulation through heat treatment to stabilize that Al3MG2 compound and prevent the formation of those brittle galvanic hotspots, while still keeping the grain refinement we need. That's the question that has to drive the next round of research.